To ask.
Hey Chris, we can see you on the big screen. If you like, you can start sharing your presentation.
Justin, how you doing?
How about time? Time for the cows to come home. Yeah, I like live stuff. Okay. Okay.
I didn't even know if it's not.
Oh, yeah, right.
All right, just have a few people streaming in.
Okay, so I think most people have streamed in from outside now. All right, so for our seminar today, I think as most people who are here know, but some people have trickled down or from somewhere else, we are having the Joint Polar Climate Working Group and Ocean Model Working Groups for the Community Earth System Model, CESM, this week. And so this morning we had a joint session about wave ice interactions, and now we have Chris Horvat, who is going to give a seminar. So the title of his seminar is Understanding Biases in the Antarctic Sea Ice Concentration. Chris is an assistant professor at Brown University. He's an applied mathematician and physical oceanographer. He leads the antipodal oceanography group, so he works on understanding, or his group works on understanding climate change in polar and tropical regions. You'll notice this is a contrast to me, who I say I just stay in the polar regions, and that is accurate. His group's key research areas are modeling sea ice fracture and ocean surface waves, parameterizing ocean turbulence and mixing, remote sensing sea ice and waves, emergent ecological variability in polar and tropical seas, and we'll have a topic about that tomorrow in the Polar Climate Working Group meeting, and then modeling of tropical cyclones and their impacts on the Pacific. His group also works on machine learning applied to climate downscaling and emulation. So Chris is joining us remotely, and you can see his picture up in the corner, and then I will help facilitate a Q&A at the end. So thank you, Chris. Go ahead and take it away.
Can you hear me okay?
We can hear and see.
Awesome. So I've got a big screen that's got the presenter view to my left. So if you see me looking over my shoulder, that's why that is. So I can't see any of you without not looking at the screen. anyways, yeah, thanks for that introduction. And yeah, really excited to talk about some of the work my lab has been doing of late on understanding the passive microwave signature, particularly in Antarctica, and for sea ice concentration retrievals. So this work will largely be stuff that I've done in concert with my postdoc, Katya Tavri, and a graduate student, Kimia Mahabanazad, who we'll see their photos in a second. I think they're both on the call. So as an outline, I'm going to use this time, a nice long hour, to talk about the kind of setting for the problems we're going to investigate. So, like, how do we understand and record sea ice coverage in the polar seas, starting from first principles? And then I'll talk a lot about the challenge we've observed in how those retrievals and inversions are resulting in sea ice concentration products. And then go on to our proposed solution, or efforts we've made towards a solution, which include the use of other sensing products and complementary data. And then there'll be an ask. So I will request assistance from all of you at doing something with all the complaining I'm about to do. So as I mentioned before, Katya is a postdoc in the lab, and she's a SAR specialist who's been working a lot also on ocean waves. And Kimia is a graduate student-ish. She is in Iran and has been unable to secure access to the United States for the last 3 years. So it's been a very interesting working relationship, but she's an excellent remote sensing specialist based in Tehran. So we're going to set the scene a little bit and talk about passive microwave radiometry from the perspective of these early figures like Ray Lejeune and Max Planck. So as a bit of a confession, this is a polar climate working group meeting for modeling mostly. I am a modeler originally. My lab is focused a lot on small scale physics of sea ice flows and the way that we could parameterize their effects on larger scales. So I did not come into my PhD or postdoc or faculty positions with any training in remote sensing, or really any understanding of how we make remote sensing products. So if everything I'm about to say to you is just absolutely dead serious and obvious, then I apologize. But if not, you're in the same boat as me, I think. So we're going to really talk about the workhorse of observations, both globally and in the poles. So these are the passive microwave radiometers, which have been in space since 1978, and there were earlier versions that did not sense in these particular bands. The most famous ones are from DMSP. There's the SSMI and SSMIS. So these are the special sensor microwave imagers and sounders that have been flying on US defense satellites. And over the last decade or more, the AMSR satellites have been launched by JAXA. So the passive microwave radiometers are the way that we sample sea ice coverage going back to 1978, as well as global mean temperatures or surface temperatures going back to that same period. And just for some perspective, because we'll talk about it in a second, this is the EM spectrum from Wikipedia. When we're thinking of microwave radiation, this is stuff with a wavelength of 10 to the minus 2 meters, so centimeter scale waves. These are long or high wavelength waves. They're not high frequency waves. Writing this talk and lecturing on the EM spectrum has led me to wonder how microwaves work, the things that heat our food. I have not figured that out just yet. Why do we need these long high wavelength waves? But someone can probably explain that to me in about 3 seconds, I'm sure. But in general, we're talking about fairly low frequency, high wavelength waves in the electromagnetic spectrum. So we know from physics that there is a representation we can do, the black body spectrum, of the amount or the power density of emitted radiation from a black body as a function of its wavelength. And this comes to us from Max Planck. And what you're seeing is an example of several different emission spectrums for different fairly hot objects. On the right, it has this functional form, and the way that we were able to derive this equation has to do with the brilliant assertion that light is quantized in the form of photons. So this was not something that was classically understood. And then once Planck came up with the idea that you could quantize photons, you are allowed to, or eventually result in an equation that looks like what you see on the left. It's the same form as a function of wavelength you can see here on the right. So we have this dependence on frequency or wavelength, and this exponential thing in the denominator of our solution, which includes things like the speed of light, Planck's constant, and Boltzmann's constant, and temperature. So we're going to go backwards from the Planck spectrum to try and understand how PM radiometers work. And I'm using PM as the abbreviation for passive microwave, and PM-SIC is CS concentration retrieved passive microwave radiometry. So this is our Planck spectrum as a function of frequency. And we're thinking of low frequency waves. Those are microwaves. So we have this really juicy thing in the denominator, an exponential -1. So for nu close to 0, we can expand that in a Taylor series and find that the denominator just resolves pretty easily. And we end up with a spectrum that looks like this for low frequencies. So temperature, a frequency, speed of light, Boltzmann's constant, and some other ancillary terms. And this is what's called the Rayleigh-Jean approximation, or Rayleigh-Jeans approximation. And the first one, the top, the Planck spectrum, is a quantum mechanical solution. Remember, light's quantized, and the Rayleigh-Jeans, Rayleigh-Jean approximation can be derived from classical mechanics alone. So these are John Strutt, aka Lord Rayleigh, and Jimmy Jeans on the bottom there. And they came up with this idea around the early 1900s, first half decade of the 1900s. So this is the spectrum, and it's something that can be derived classically. So you think about the number of wave modes inside of some spherical shell, and you can arrive at this equation. It has this quadratic dependence on frequency, and it's linear in temperature. That linearity in temperature is not a problem, but the quadratic frequency dependence is a big problem. It gives rise to something called the ultraviolet catastrophe, which we'll talk about in 1 second. So this is your spectrum. You have this quantum frequency dependence of radiation, and the classical spectrum goes up like the second power of the frequency. And so this was known as the ultraviolet catastrophe, or at least that's how it was taught to me as a physics student. And the nice thing about low frequency behavior is that the amount of radiation is approximately linear with temperature. So this is what we're going to exploit for understanding sea ice coverage and indeed temperature, surface temperature across the globe. Interestingly, even though they taught us, at least I recall being taught, that the ultraviolet catastrophe was this big problem, and Planck came along and created quantum mechanics in some fashion and solved it, Planck came up with the idea behind that spectrum before Rayleigh and Jeans did. Incidentally, they didn't publish that result until 1905. They were talking about it in 1900, but Planck published the Planck spectrum in 1900. So it's one of those weird curiosities of science that the strange man Max Planck came up with the quantum solution before we knew really that there was a classical problem. So kind of a fascinating little aside there. So anyways, passive microwave satellites are measuring radiative emissions from the surface. And when we observe radiance in the atmosphere, at the top of the atmosphere, we have this spectral emissivity, and the spectral emissivity just modifies the observed, so the expected outgoing spectrum by some factor. And we can approximate this using, this is what gives rise to what's called a brightness temperature. So we assume that epsilon times S is just epsilon times the low frequency Rayleigh-Jeans approximation. And then we just lump that epsilon times the temperature as the brightness temperature. So this thing is what passive microwave radiometers are measuring. They're measuring spectral radiance. They're dividing out these prefactors. They have a fixed value of the frequency. And so they're sampling brightness temperature, which is not a temperature, but an effective temperature that would give rise to an equivalent amount of emissions. So that's how they work. And sea ice, amazingly, is so easy. And the reason is that sea ice and the ocean have very different brightness temperatures. So you can imagine that if you have some sort of swath underneath your satellite and you see the water next to the ice, well, ice is cold and the water is warm. And so you can derive this estimate. So depending on if I know what the ice surface temperature is and I know what the water surface temperature is, I can do some very simple linear combination and obtain the fraction of the absorbed radiation that's coming from ice and coming from ocean. Interestingly, this is not true. Of course, there are situations where the water surface temperature is close to the sea ice surface temperature, but the idea that the water is warmer than the sea ice is incorrect from a radiometric perspective. And here's why. This is an example of answer 2 brightness temperature earlier, or I guess at some point last year. And sea ice is much hotter electromagnetically or in the microwave than the ocean. So it is not that the sea ice is cold and the ocean is hot, but actually that the emissivity of the sea ice is much higher than the emissivity of the open water. Doesn't matter. We see the ice as a direct contrast to the open water in images like this. So they're differing by 100, 200 Kelvin in terms of their observed brightness temperature. And so the ice is hot, the ocean's cold, the land ice is also cold, incidentally, and we can use this to separate them in some linear way. So that's what we do. Seawater emissivity is about half, less than half that of sea ice. And so we form these kind of linear relationships between the brightness temperatures we observe and the brightness temperatures we expect from the ice and the ocean. So the idea that we could use, I mean, buoyed by images like this one, the idea that we could use the difference between ice and ocean to classify the sea ice surface is not a new one. It dates back to Joey Camiso's original work in 1979 and probably folks before that as well. And the idea is if you take a scatter plot of brightness temperatures with different polarizations and different frequencies, you can separate different ice types and you can separate them from the ocean. So this is a parametric plot of the 37 gigahertz vertically polarized brightness temperature on the x-axis and 18 gigahertz vertically polarized brightness temperature on the y-axis. And you can see that most of the points classified as ocean lie in some cluster, then all the ice lies on some other very straight line sort of cluster. And it's a mix between some ice and some ocean. And by drawing lines between various tie points, you can obtain a sea ice concentration. So this is what these do. The most common and most heavily relied upon algorithm for sea ice concentration retrievals is what's called the Bootstrap algorithm, which I think is so named because it bootstraps the estimates of these straight lines based on the data it receives. This dates back to 1979. And if you use the NISAR climate data record, which is probably, at least in the United States, the most commonly used product for sea ice concentration, almost, well, more than 95%, it's like 95.1% of all of the data that's recorded comes from Bootstrap. So this is the workhorse, and even the other climate data record from OCSAF is also using Bootstrap data for a significant portion of its available sea ice concentration estimates. So that's what it is. That's how this works. And there's key issues associated with these multilinear style regressions, which have to do with the tie points you choose, the weather filtering you do, the footprint size, contamination by land, all sorts of other complexities that give rise to the spread you see here. So just as an example from that same spot before, here's our diagram in Antarctica, the same Camiso diagram, we're calling it, from answer 2. This is 2 different polarizations. This is 36, not 18. But you can see in one horizontal and one vertical polarization, still significant differences that allow you to separate between different ice types and features in the sea ice, and you still obtain this kind of semi-linear relationship. That green histogram part would be ocean, and all the other stuff would be ice. And the inference is the ice, or the 100% sea ice concentration is up to the northeast part of this. So that's how it works. And passive microwave radiometry is the most important thing we have for observational constraints on sea ice. It has been the thing that we use to observe the Arctic sea ice decline as well as the Antarctic sea ice decline. And you can see the monthly anomalies of CDR-based sea ice area in the bottom. And you've seen this rapid swing since about 2012, first a growth phase of Antarctic sea ice area, and then rapid declines in Antarctica. And the spatial distribution of those changes, at least in this Financial Times plot up till I think 2022, maybe 2024, is kind of heterogeneous across Antarctica, but largely concentrated on the margins. And all of this comes from sea ice concentration data from PM. So that's our lesson for today. And now we're going to think about whether we trust all of these retrievals, particularly in Antarctica. And the discussion of whether or not we should be using algorithms like Bootstrap for Antarctica is an open one, but that's not the only algorithm that's been designed for Antarctic sea ice or just general sea ice retrieval, but most of them are being used and constrained on data in the Arctic. So we'll talk about what the implications of that might be. And we're going to do that by initially comparing two different completely independently developed or largely independently developed products for sea ice retrieval. One is the NASATeam2 algorithm, which exploits a higher resolution part of the spectrum from AMSR2. This is a new set of satellites, AMSR2, that's launched in about 2012. And then this is going to be compared to the climate data record that we're all fairly comfortable with. This is the difference between those plots on a random day, an actual MATLAB selected random day in 2023. And what you can see is there's a big difference in how they represent sea ice area for this day in October. The purple means more sea ice in NASATeam2, which is aiming to sample thin sea ice, and less sea ice in the CDR, though there are some smaller differences in, say, the Ross and Weddell seas. So the overall difference between these two plots is about 1.3 million square kilometers of sea ice, again, just some random day, and that's 8% of the total sea ice area. A less random day, I just selected one that was in at the end of the melt season. This is in March of 2023. And here, the difference in total sea ice area is about 21%, and the areal difference is about 500,000 square kilometers. So here are two algorithms designed by groups both, largely branching from NASA-based work or NISAR-based work, who are showing really significant discrepancies relative to the large-scale trends in Antarctic sea ice area just on any given day. So which one's right, and how do we improve the other ones, or are they both right? Good question. So one thing I want to head off, because this frequently comes up when we talk about these biases, is that intercomparisons looking at the climate data record against other products have often claimed that sensor issues. So the footprint of a sensor from the climate data record based SSMI stuff is about 25 kilometers. The newer satellites are higher resolution, and that has been invoked as a reason for why these differences might emerge. Because if you added up the sea ice marginal ice zone, or the edge, not just the marginal ice zone, but the actual periphery of the sea ice zone in Antarctica, you could conceivably come up with a bias correction that's of the same order as these discrepancies we're seeing. But these algorithms are easy enough to implement, and in fact, most of the groups developing these products do. And you can actually just evaluate whether, if we use the climate data record style sea ice concentration algorithm on the higher frequency, higher resolution footprint, you end up with the same issues, and you did. So this does not appear to be related to the footprint of any of our sensors. It has to do with real discrepancies in the retrievals, and I'll get into more details on that in a minute. So great, we've shown some plots with some purple and yellow things, but the ultimate question is, does this matter? And the first thing to note is that Antarctic sea ice extent is incredibly consistent between all of these products. So what you're seeing here is Antarctic sea ice extent over the ISAT2 period for 4 different products. The climate data record is in black, you can't even really see it. The NASATeam2 algorithm on the AMSR data is on green. The AMSR2 climate data record equivalent is in orange, and then an SSMIS-based one, which doesn't use the other half of the climate data record, so something like the climate data record, is shown in puce, purplish, bluish purple. And so they're all very similar throughout all months. And this might seem calming, and maybe it is calming, but it's also by design. The development of the later algorithms were always calibrated against whether they perform the same on sea ice extent. So this is good, and generally speaking, the question is, does this metric obviate the need to worry about these other biases? So let's think about it. Here we're looking at the bias between, again, the CDR product. And this is in all months at all times in Antarctica. But now, if we think about sea ice area instead of sea ice extent, the product bias we're showing here, this second plot on the bottom left, is looking at the histogram of typical differences between the climate data record that we often use and this particular product from NASATeam2 on the AMSR2 satellite. And you can see typical offsets are about 900,000 kilometers squared. So that's about 10% averaged over a seasonal cycle of the total sea ice coverage in Antarctica. So this is fairly large, and what you can see is that this concentration difference, if we average over, this is averaged over the entire period, it appears to be most significant in the marginal ice. And if we just compare the interquartile range of this bias, so the interquartile range of sea ice concentration to this bias, we find they're small, which is leading us somewhere, which is that in places where the sea ice is varying, the IQR would be larger, and the bias is larger in most cases than the IQR. So when the sea ice moves, or when the sea ice is varying, you have higher biases. The bias is greater than the interquartile range of the sea ice concentration bias. So that leads us to do something, which is deseasonalizing the data. So instead of worrying about the areas where there's 100% sea ice concentration, where it's easy to make these sea ice concentration products agree, we look at only the points where you don't have 100% sea ice concentration. And this is what the difference map looks like. It's a remarkably consistent whole Antarctic bias offset of between 20 and 25%. This is two independent sea ice concentration products using different or the same sensors. It doesn't really matter much. And if we compute something like the marginal ice zone extent, so the area where the sea ice concentration is between 15 and 80%, the climate data record and this NASATeam-based product differ by several million kilometers. So all of this is coming down to the decision about, in areas where there's some open water, how much open water is there? Is there more than 20%? That's what the CDR suggests. Is there basically none? That's what the answer-to-based NISAR algorithms suggest. So all the action here, all the interesting stuff here happens in discriminating between whether there's open water or not, which is also how we decide about, say, the air-sea exchange in polar regions, or where all that's happening. These uncertainties are, we showed here, kind of deseasonalized, extremely significant, are very consistent, but they're much larger than the published uncertainties available in these products. And this should give those of you who are using these for model comparison or data assimilation or state estimation significant pause. So oftentimes, climate data records like PM-SIC is treated as an observation. But if we look at the inversion uncertainty, that's what we're calling the difference in the inverted sea ice concentration from the climate data record versus this other algorithm. The median difference is 19%. So the median uncertainty associated with two different algorithms applied to the same data is almost 20%, or 0.19, sorry, that's the sea ice concentration difference. But the uncertainty is 30%. So because sea ice concentration is a percentage, sometimes when we report differences, it seems like we're talking about uncertainty, but the difference is 0.19, and the uncertainty, the average misfit is 30%. This is the bias, sorry, this is the uncertainty that would be produced from the climate data record, which does publish an uncertainty estimate. And the x-axis here, sorry, is the sea ice concentration from the climate data record. The y-axis is the bias between the algorithms. And you're seeing the parametric uncertainty associated with the inversion of passive microwave brightness temperatures compared to the reported uncertainty in the climate data record. So it's significantly higher in almost all parts of the sea ice concentration range. So if you're ingesting CDR data and you're using published uncertainties that are gridded with the sea ice concentration data, this is something to be aware of. It means that it may be difficult to separate process uncertainty or your model uncertainty from passive microwave inversion uncertainty, which seems to be twice as high or larger across much of the sea ice concentration range, and in fact, the sea ice concentration range where the interesting stuff happens. So I'm going to explain to you, I haven't really articulated why we're making this data comparison. It's a bit cart before the horse, but I'll show you in a bit. But also I want to say that we have started to examine the impact of this uncertainty for global ocean state estimates. So this is the global overturning stream function from ECCO V4R5. ECCO is a data assimilating global ocean state estimate that also has an adjoint. And so we perform a single iteration of ECCO. We recalibrate the input parameters and run again. So we have a difference between, and what we're doing as an input field is we're shifting from the CDR-based sea ice concentration to this adjusted or this higher sea ice concentration regime. So we're just exploring sort of like an A/B test of the impact on global ocean overturning between those two things. And we're targeting a very small reduction in the sea ice concentration loss from the forward step of ECCO. So we're not really modifying the sea ice fields very much. We're not asking ECCO to match the sea ice concentration fields very greatly. And sorry. So we make this small adjustment to sea ice concentration. We form a single iteration of the model. And what you can see is the initial, so single iteration, non-optimized impact on global ocean overturning. So it's strengthening, it's shifting the wind-driven ACC. It's probably strengthening the Antarctic bottom water cell. And it's doing that at the order of 5% relative to the baseline. Remembering that we're doing a very weak, we're not actually in an optimized state estimate. So we don't know just yet how much the difference in the state estimate will vary over time. It could increase, it could decrease as we move towards recalibration of the input parameters. So just to say that this does make an impact on deep ocean overturning in forward runs of ECCO. And it has these kind of strange effects. So on the bottom, we're looking at, on the left, this is the global ocean temperature, volume adjusted, volume integrated temperature. And we're looking at forward runs over the 1992, which is the initial branch of ECCO. And red is if we adjust for the LIF, which I'll explain what that is later, and use the standard CDR is in blue. And so in general, the simulations that have higher sea ice concentration for a short while have less global mean temperature or global ocean temperature, and afterwards heat up more. So that's the black line. It's the anomalous difference in global ocean temperature between the high sea ice concentration and the low sea ice concentration. So both ends of that thing. In the Southern Ocean, this doesn't move as much. So the Southern Ocean stays slightly cooler. And this is an interesting feedback response, probably associated with redoundal overturning that we haven't really had time to explore very much. The appealing thing about ECCO is that you can do these adjoint sensitivities of any quantity of interest to anything else, basically, that's in the model, any other constraint. And so what we started looking at is the relationship between meridional heat transport through a gate. So this is the South Atlantic gate, and other aspects of the sea ice and heat flux field. And I don't have a lot of interesting things to say on here, just to say that there appear to be impacts of increasing sea ice area, especially in the Weddell Sea, on meridional heat transport, which is not exactly all that surprising. So I'll pause there if anyone has any burning questions about that, and then talk about what we're doing with remote sensing products to implement some bias corrections to this, or improved understanding of this bias.
Clarification question, maybe.
I can't hear very well, sorry.
I said just for clarification questions, but it looks like nobody has a burning question. So I'd say continue, and then we'll have time at the end.
Cool. Okay, so we're going to look at sea ice now. And this is a SAR image in the Bellinghausen Sea, so west of the Weddell Sea, west of the Weddell Peninsula. And this is Sentinel-1 SAR. And what we've done in a number of cases is perform SAR-based classification of this surface. This is largely led by Katya. And we can compare the two different estimates that we're saying are the range of our potential biased sea ice concentration products, the CDR and the SAM2 Bootstrap sea ice concentration. So the scene is this thing on the left. The red outline shows the area of that scene, and you can see the colors. On the left, it's the SAR sea ice concentration, and the two other ones are the two different passive microwave-based products on the same time. So you can see there's significant variability, but I've already talked about that. There's significant changes. It's up at scales larger than the footprint scale of the passive microwave data. So if we zoom in on the climate data record sea ice coverage, this is what this looks like. And we're lucky because in many cases we have intersecting tracks with ISAT2 of the CDR data. So this is an ISAT2 track. It's the first one I'm going to show, and maybe the only one I'm going to show. And what you're looking at is on the x-axis, this is moving from the open water, so from the Southern Ocean to the sea ice and eventually to the land ice. So we're moving north to south from left to right. And the plot here is surface height from ISAT2. It's not freeboard, it's the measurement of the free surface. And those individual points you see here, this line plot is actually individual returns from ISAT2, so footprints of ISAT2. And what you're seeing here now is the mean and interquartile range of those values. So as you move from the open ocean into the ice, these are all ice points, by the way, the dashed lines are showing a decrease in variance, but high negative amplitudes, and those are a signature of ocean surface waves. These are waves in the sea ice. We can compute along track a series of different metrics for when the sea ice becomes compact, so when the sea ice concentration reaches 80%, using both SAR classification, ISAT2 base metrics, and ISAT2 base metrics. And we can compare that to what the passive microwave product says. So when does the sea ice hit 80% as we move into the sea ice zone? This is the climate data record edge is green, and you can see in the top right the location of the track. You can see with your eyes that the sea ice is pretty far out there, and we're talking about a 50-kilometer or so difference between when the sea ice is determined to be compact in the passive microwave related products and the ISAT2 base reconstruction or the SAR reconstruction. So ISAT2 is orbiting and has been orbiting since 2018. It does 14 total orbits every day. So that means because of the symmetry of Antarctica, we get to intersect the sea ice zone 28 times every day. And I say 168, how does it work? Oh, because there's 6 individual beams. So there's 6 beams on ISAT2, 28 times 6 should be 168. And that means over the course of the ISAT2 lifetime, up until we wrote this paper at some point last year, we had more than 400,000 intersections of the sea ice zone. And what you're seeing here is the number of tracks, that's in pink. And we're taking, for each track, we're taking the point at which the climate data record of sea ice concentration measured along track hits 80%, and we're centering that to 0. So we're compositing all of these tracks on the marginal ice zone edge as obtained by the climate data record. So ISAT2 is sampling many, many times an area that the climate data record says is the marginal ice zone, tens of thousands of times at least. So before we try to look at that composite map again, I want to articulate something that we've worked on a lot in my lab and with colleagues here at Brown, which is the development of a sea ice concentration product from ISAT. And it's called the ISAT2 linear ice fraction. It is as simple as it sounds. We take the length of ice segments and divide them by the length of all segments. Of course, we do a lot of quality control. We have a whole paper about bias correction and understanding the uncertainties associated with this product, but it has some benefits. One of them that I didn't mention is the sea ice concentration is bounded, which wouldn't be true for the multilinear regression. And it has this really high frequency sampling, so it sees fractures that might not be picked up in the passive microwave products. Obvious drawbacks are that it is a 1D measurement, and you have the sparsity of data associated with just 28 intersections per, or 14 orbits per day. So I won't get into all of the efforts we've made to constrain this product, but in general, we know that it picks up fracture features and it outperforms passive microwave data, even in single passes in the Arctic. We can reduce biases for high concentration sea ice significantly by using an ISAT2 based product. And we have pretty good coverage. Because of this return sampling or the infrequency of sampling, we're not really able to produce daily or high frequency and time products, but we can produce monthly gridded data for about half of the Arctic sea ice zone and about half of the Antarctic sea ice zone. So that's pretty good. It's not a competitor to the sea ice concentration climate data records, but it is something we can use to do confirmative analysis against them because it offers an independent and largely bias-free estimate of the sea ice coverage when sampled enough times. So we make this broad scale comparison against many, many images taken of, this is actually going to be a comparison between the linear ice fraction and the climate data record in the Arctic. And what we can see is that there's this mean offset bias in the climate data record products against the ISAT2 based product over something like 200 or 300,000 intercomparisons, so grid scale intercomparisons in the Arctic. In general, we find this with most of the sea ice concentration products, and this matches a known overestimation bias at high concentrations by the passive microwave products, namely because they just can't sample the high frequency openings like leads and thin sea ice that ISAT2 can do. So in general, in the high concentration regions, we find that there is more open water than is suggested. But what we're going to look at here, I'll skip through this, is a different area where the climate data record is saying the sea ice concentration is not 100%. So here's what this looks like. if we look at these samples along track, we're now, remember, aggregating all of our along track linear ice fraction estimates from ICET2. We're moving into the marginal ice zone on the left, so negative values are the MIZ is observed by a typical passive microwave product. And we're seeing much higher sea ice concentration estimates from ICET2 there. And that bias is represented by this dashed greenish blue line, and it's about 21%. Luckily, the CDR is not the only record of sea ice concentration. We also have that same ANSWER2 NASATeam2 algorithm we were looking at before. And lo and behold, it is nearly identical to, at least parametrically, to the ICET2 base record. So ANSWER2's sea ice concentration record in lower sea ice concentrated areas in Antarctica appears to match exactly what the ICET2 altimeter says is happening there as well. So this upper estimate that we were talking about before, which indicated potential uncertainty in the passive microwave record, may be a good estimate of marginal ice zone sea ice concentration across Antarctica. And this inversion difference, this is the comparison on the left now, the x-axis is the climate data record, the y-axis is this NASATeam2 algorithm, appears to be fairly consistent. We don't have huge outliers, it's readily parameterizable, and it matches nearly exactly to the offset we see, at least in the marginal ice zone, from ICET2. Both products incidentally underestimate, or sorry, this same product greatly overestimates the sea ice coverage in the marginal ice, sorry, in the high compact ice zone. So we can parameterize this bias. Now we've just added this dashed blue line, which is a quadratic fit to the uncertainty, which matches the ICET2 base uncertainty between the climate data record and the ANSWER2 record. So our suggestion is that this could be used as a correction for the marginal ice zone, at least for broad areas of Antarctica. And the implications are large. So depending on how you define the marginal ice zone, if you use the climate data record and you use the climate data record to constrain, say, wave-related simulations, you will get much broader MIZs than you would using a concentration-based definition for the ANSWER2 product or the linear ice fraction-based ICET2 corrected product. Both of them appear to be uncorrelated with ICET2-based wave information. So that's something that's been observed by Alex Fraser and colleagues, that it isn't always the case that the impact of waves is one-to-one tied with the impact on sea ice concentration, which makes sense. So that's it on the complementary data. And I'll spend a few minutes just talking about what we're trying to do next, and then the ask for all of you. So hopefully from the last 40 minutes, we've developed 2 open questions. The first open question is, what the hell is Chris talking about? That's a good one. But the next one is, how much do these biases matter? How much does the fact that the thing we actually are comparing our models to exists as an inversion of an actual observation? So there is a model that translates the observations to the physical thing that we are then comparing our models to or assimilating. And the uncertainties may be large, but do we care? And then the second one is, can we do better? So can we make our climate data records better, either using complementary data, these kind of bias corrective mechanisms, machine learning if you want, and how do we do that? So that's what our focus is, at least on these style of products. And we're really trying to work on this improvement right now. So we have a paper about explaining this bias correction that is in, well, I think I projected, so we're resubmitting it. And we're working with complementary products from SAR and NISAR and things like that. But the area that we really think would be really great to work on, where I think I personally lack the expertise, is understanding how much these might make a difference in both forward climate simulations for intercomparison, or a lot of our assessments that we typically make with models, and in particular for data assimilation. So models that assimilate sea ice concentration data, if you were to change your assimilating framework to shift the sea ice concentration higher in Antarctica, how much does that affect the perceived state of Antarctic or general polar climate? We'd also like to work on the improvement of these data with people in the room too. So in terms of how we're working to climate data records, we're very lucky. There was this really neat article written in Nature a few years ago about how the NISAR mission, which was launched last year, is south-facing, which I didn't know until they launched it was a thing that satellites can do, but it only faces south, which if you're an Arctic scientist stinks. If you're an Antarctic scientist who just found out that you're going to get tons and tons of SAR data from the satellite, it's great. And so this mission has lots and lots of available SAR data. Most of the data that's been published is over land right now. That's what Katya let me know this morning. But we have lots of available SAR data for confirming things. We've been working in the Arctic with Kimia on developing classification schemes using expert-generated ice charts. And this mirrors efforts in AI for Arctic and Ice Bench, which are really cool efforts to try and do automated classification of SAR. It's a really challenging problem. And our focus in our Pacific work largely has to do with transfer learning. So we're hoping we can take the methods that we're developing there for transferring data from small island states to or US islands to the Pacific small island states and do the same thing. Take our automated classification schemes in the Arctic, maybe change F to negative F, in a machine learning sense, and then translate those to Antarctic classifications to improve the CS concentration retrievals. And we're working with the ECCO group, so Patrick and Ann at Texas, or part of the ECCO group at Texas, to try and build a CS concentration product directly from passive microwave brightness temperatures, not from passive microwave inverted CS concentrations. And also, I should say, we have a gridded linear ice fraction product, NISATeam2 product, and we have a bias-corrected sea ice concentration product. The linear ice fraction product is open and is available since 2018. Our preliminary corrected global sea ice product would go back to 1978, but it's by request because I don't think it is ready for, we don't trust the output just yet, but we'd be willing to work with folks who are interested. And just an example, this is data from Kimia's project. So that's a Canadian ice chart, and we're taking things like CS concentration and development stage, all obtained from experts, and trying to use that with coincident SAR imagery to do forward projection, or sorry, forward classification. So here's an example of that in progress. This is an example SAR image in, I think that's Nunavut, maybe. And there's predicted ice classes. We're just doing sea ice, open water, and land right now. And it's a really challenging problem, but it's fun. And we're still working out how to do this well. And then finally, I mentioned NISAR. NISAR is really cool. It's LNS and SAR. It does lots of observations. It will see the Antarctic surface all the time. This is really neat. And we just are hoping for the data to come out for Antarctic data, for the Antarctica. So then finally, the question of how much do these biases matter? We think they matter. Very simple tests with ECCO appear to show pretty dramatic changes in ocean overturning associated with just modifying sea ice products. But we want to do a lot more. So there's lots of assimilating systems that people are using. There's lots of model comparisons that people are doing. Can we assess CMIP model skill? There were these really cool papers from now about a decade ago looking at the histograms of sea ice concentration output from sea ice models largely focusing on the Arctic. But what if we did that in Antarctica? There was the sort of compact versus loose sea ice model, but maybe the compact models are actually the right ones for Antarctica because of this thin ice problem. And ECCO allows for these really cool adjoint sensitivities, so it doesn't actually do direct, say, nudging of oceanographic or sea ice fields. So that means we can do physics-based simulations that we can then constrain using the adjoint. So we want to do a lot more of these. Love to do them with the modeling centers that are there, particularly NCAR and DOE, and yeah, just really excited to think of ways that this might or might not impact global climate. That's it. So I came here to bury Caesar, bury PM, not to, I don't know the phrase, but the passive microwave data is an incredible resource. It dates 40 years. It's amazing. We can learn a whole bunch about it, but we should be careful about its application, mainly because of these uncertainties in Antarctica, and hopefully other orbiting sensors like SARS and ISAT2 can be used to improve this data and make it more readily understandable for assimilation and state estimation. Thanks.
Thank you, Chris. So I'm going to take some questions. The overhead mics are on, so you should be able to just speak. I got a text message question, so I'm going to start with that one. It is from
Okay.
Jana Shaw. Hi, Chris. What about directly simulating the passive microwave observations in our models and comparing radiances with observations or performing an identical retrieval to avoid structural uncertainty in your retrievals?
I don't know who said that, but hell yes, that is one of the focuses we're trying to work on. There's SMART. There's this like snow microwave radiative transfer model that's been implemented. So I think the hope is that we can do forward modeling and make observations-based comparisons. So that means comparisons in brightness temperature for assimilation rather than in sea ice concentration, for example. We think that, at least from some early testing, that, for example, if you were to look at reanalysis products from Era 5, the Era 5 quote-unquote brightness temperatures and the observed brightness temperatures are very different. And that's because of the fact that they're assimilating sea ice concentration into their reanalysis products.
So Chris, that was from Jonah Shaw. Jonah, if you're listening, you can email Chris for more information to plan it. All right.
Thank you.
Any other questions in the room? Start with Alec.
Thanks, Chris, for a great talk. I have lots of questions, but I'll try and limit it. I'll just stick with this one. So you talked about the ocean impacts of those concentration biases. I maybe missed what the actual process is that's driving that, and is that a better thing to constrain instead of concentration?
So the ocean differences we saw, again, these are just from single iterations of ECCO. So we have to be very careful about reading too much into this. But you can just sort of think of it mechanistically, right? If I add 20% sea ice concentration to Antarctica, in this case, it's like 2% or something, I'm going to shut off Antarctic bottom water formation, and I'm going to move the location of the wind-driven ACC northwards. So you have these two competing effects. There's two overturning cells in Antarctica, and you're going to modify them. So I think that's basically what we're finding. We were prepared for a result that said nothing happens, but a sort of 10% shift in Antarctic bottom water production for a 10% bias correction in sea ice concentration seems pretty significant. So that's kind of the mechanistic meaning. I don't know, because we can't test the like Argo against sea ice or not sea ice, or like one sea ice product versus another. It's hard to do testing on with observations in the ocean, I would say, but we could definitely evaluate changes in their impacts and sort of quality against Argo, though ECCO is probably not the framework for that because ECCO assimilates Argo.
Molly, I saw your hand next.
Yeah, hi, Chris. This is really neat, and I think the data assimilation's implications are really interesting. Are you willing to say anything about why you're dissatisfied with your bias-corrected global product?
Because we have parametric plots. So we have plots like this, like we're doing this kind of bias correction, but all of that, the problem with PM, at least as we see it, is this uncertainty that might be parametric. So we've explored one particular parametric part of this, but do we necessarily trust that our quadratic fit to this bias is a good idea? I think until we know, we're not doing any physics-based like estimation of this bias, and realistically it should be based on the physical properties of the sea ice, right? So that's why we're trying to do this brightness temperature sort of emulation or forward modeling part. But yeah, so we can provide this with I don't want to publish it or like put it online somewhere where other people will ingest it and then treat it like it's right. I think that's basically the hesitance, is that I wouldn't want that to happen and have it completely fall apart when we actually learn more about the physics. So.
All right, it looked like there was a Slido question here. Do you think GNSS reflection data can improve sea ice concentration mapping? I don't know what GNSS reflection data is, so you'll have to, hopefully you know.
I have to say I also don't, but I think the answer is yes.
Okay.
Probably. I'm going to say yes, but I've never used that data set.
All right, other questions? Alec has another question.
Sorry, Chris. you kind of touched on this, I think, but yeah, passive microwave isn't good for detecting waves within sea ice, but are there other frequencies that could start giving us some signals about wave-affected regions within the ice pack?
Yeah, so we do find a pretty strong correlation between this bias and waves, which is initially what we're really excited about, was that the differences between PM products was associated with waves. And it turned out that actually, if you took away the wave-affected ISAT2 retrievals, it was still there. So it probably has more to do with thin sea ice. There's been really cool work. I don't know if Noah's still on, but Alex Fraser at UTAS has done a lot on the use of this other satellite called Antarctica, which is a Russian satellite, I think. It's a K-band, AA-band SAR. And it is like incredible. Like there is this weird, I don't really understand it, but you can peg the location of waves to some curvature properties of the retrievals that, again, I'm not really sure I understand very well, but they appear to be really well correlated with instances where ISAT2 sees waves. So I think that might be the next stage for really trying to do model comparison, because I think Antarctica has better coverage than ISAT2.
And for everyone's reference, GNSS, says the internet, is Global Navigation Satellite System. All right, David Clemenceau.
Hey, Chris. Really great talk. Nice to see this coming along. I was wondering if you've looked at all about potential biases for the thin ice, whether it's growing versus melting, and if you see any difference there.
So we see no seasonality to this offset. We haven't looked at so that offset between the two products appears not to be seasonal. It just appears to be parametric. So it really just depends on the CS concentration fraction. So or the CS concentration estimated from the Bootstrap algorithm or the CDR. And so in winter, you have just much less of these low concentration regions in Antarctica. So there is a seasonality induced by that. If you were to look at the sea ice area maps I showed at some point in here, the offset declines as a function of it's largest at the minimum, but it's smallest in like the shoulder seasons. And I think that has to do with the fact that you just have less medium concentration ice as recorded by the climate data record. So I think it still emerges at the peak. So you can see that like in the winter months, that's where the largest area-based difference is. And that's kind of odd because you see a map that looks like this. You have these large swaths of the MIZ where the climate data record is saying there's less than 80% CS cover. That example, actually, that was a February image, the SAR I showed before. So that'd be summer. But yeah, so I don't know if it has to do with like surface wetting from melt, if that's the area that's what you're thinking about.
Yeah, or desalination versus.
And that's the point, is that it could be those could both be happening, right? Like both of these, any one of these physical processes could be playing a role in changing the surface emissivities and kind of screwing with some of the algorithms. But yeah, that would be why, what if there's two different mechanisms at different parts of the year? Yeah, being careful about exactly what we're saying is responsible for this is important, I think. And I don't know.
Other questions?
I had another quick one. The others can go.
Anyone other than Alec is the last call? No, okay, Alec Petty has the last question and then we'll go to lunch.
Maybe it's a bit of a group question as well, of like, so we have in size a single emissivity, but could we start introducing, I don't know how we would do this, but a different emissivity for very new, potentially grey ice that has very different radiometric properties to the other thickness categories? And would that help with some of these comparisons, especially if we start moving towards brightness temperature simulation?
Oh, I was just going to say we have a couple things you could base it on, like ice age or salinity.
So the short answer is yes, we could try that, and we probably have some tracers or model variables that you could use to do it. Maybe worth a test. All right, Well, thank you so much, Chris, for the presentation and joining us remotely. Thank you all for being here. The Polar Climate Working Group and Ocean Model Working Group will reconvene in here at 1:25 and yeah, go have some lunch and refresh yourselves and go outside. It's actually a really nice day if you want to go on a hike. Thanks.